Audio track unavailable. Alright, we going? We going? I think we're going. So, just gotta check my levels, make sure everything's right. Go over to YouTube, make sure I'm actually streaming, because the first ever stream I did, I wasn't actually streaming, and so I talked to myself for an hour. And that was not fun. I just kind of sat here and chat for a while, you know? And it says I'm live, so I'm gonna believe it. Alright, what is up, everyone? It is our stream, and dramatic music, awesome. That hit it perfectly. But we are back to talk about drives, our most favorite topic, and today we are doing... That's loud in my ears. Is that loud in y'all's ears? But we are talking about my favorite topic, Siemens drives today. Not specifically just Siemens drives. The stuff we're going to be talking about is going to be our second class of our drives 2 class now. So introduction to just drive topics in general. So if you were starting out in your automation journey and just starting to work with AC VFDs, then this is going to be a good class for you. If you weren't able to catch the other live stream from last week, I would definitely suggest going through and doing the 101 class for sure. If you've worked with VFDs a little bit, you'll definitely be able to get stuff out of this. And we have our resident people in chat already here. It's great to see everybody that is coming in. If it is your first time coming in, be sure to drop a hey in chat. And if it's not your first time in chat, welcome back. I'm glad that you are supporting the channel in all the ways that you do. Ignatius, all of the Ali Reza, Simeon, Ignatius, they're three that I see a lot on chat, and kind of know that they're always trying to do their best. Although Ali Reza apparently suffers from insomnia, because he definitely is staying up way too late to watch these streams, but I appreciate it. So today we are going to be talking about our new drives topics. I say new drives topics. We're going through and kind of continuing what we started last week. I'm closing out on this other screen my little stuff that I was using to prepare to make sure that I wasn't going to make a fool of myself. But this is your first time to the stream. My name's Jason Watts. Got 20 or so years of experience working with Siemens drives. I own and run a little automation company out of the southern United States called Alpha Industrial Technologies. And one of the things that I love to do is to help people kind of learn about automation and learn about cool projects and how to really impact their local lives, the people around them. And honestly, I mean, why do we ultimately do all of this sort of stuff? It's to make a living and to be able to provide for ourselves and our families. And yeah, I have found that one of the coolest ways to do it is through automation and going through and learning constantly. And so that's what we're trying to do here. So welcome to the stream. I appreciate you coming. Like I said last week, kind of dressing up a little bit, taking myself a little seriously. Kind of got the coat on today, because we're going to class. We're talking about drives, and I forgot to get my little paint pad up. So let me get everything. I was like doing the making sure all of the stuff was set up in Portal, and forgot to set up all my other little things that I use on the stream. So I'm glad that for those that have come in early, I'm glad that you're here. And I will try to be there we go. That kind of works. So yeah, hopefully you had a good weekend. Hopefully you were able to enjoy some. Hello, Ali Reza. Hopefully you're about to go to sleep. Hopefully I don't put you to sleep, right? But yeah, so I got that going. So one thing I wanted to mention. I finally got our membership levels kind of set up. And one of the things I wanted to introduce to you about the membership offer, I'd kind of mentioned it on previous streams before about getting it set up, but I wanted to make sure to be able to provide you with something valuable if you choose to become a member of the channel. And those memberships are live, so what you will be getting is, depending on which level you choose to support the channel at, if we do any sort of files that we create on stream, the highest level you'll be able to get everything that I make on stream. So we're using version 17 of TIA Portal, and so anything from TIA Portal version 17 up, you would be able to use these files. And we have a lower level to where I'm going to be making an archive of the PLC data types that we make and those sorts of things, and you can have those as well. And that's at the lower tier. I call it the supporter tier, and those are available on a Google Drive. When you sign up in a membership, there it's instructions, and the Google Drive link will be there. So if that's something that you're interested in and would find valuable, it's there for you, and I'll be keeping all that updated. For kind of, since this is late in the month, I'm gonna let all of the April stuff and May stuff be available for anybody that joins in April or May, or are members in April and May. And I've also added in some of the previous live streams, like the project file for the winder, the project file for the ALM, and there's some pretty cool stuff, custom telegrams and stuff that we've done there. So those will be available to you. So that's what the memberships are about. And so there's my spill. Let's talk about drives. So I appreciate everyone that supports this channel. And again, we've been growing pretty quickly. I feel. I mean, I feel like it's been a steady growth, a good growth, and organic, I think is the term. I mean, I don't know how viral industrial automation topics will ever be, but I feel like the people that are coming into the channel are really excited about it. So thank you for all that. So let's get started today. I've got my water. I've also got my coffee. I'm probably going to switch over to the coffee being primary because, yeah, it's Monday. So last week we came through and we talked about essentially the basics of VFDs. So their construction, how they're made, and just a really quick overview that I wanted to bring up was that, remember that we have this kind of three sections of our VFD. We have some sort of AC to DC, and then we have a DC link, so capacitors plus minus, and then we have our inverter. So we have our inverter bridge like this, and it controls out to our motor. And so we have our three phases coming down to our motor. And so this is the structure that for most VFDs that you will run across, this is what you're going to get. So 3-phase in, 3-phase out, but this is a fixed frequency. So 50, 60 hertz. And this normally out here ranges from 0 to 300, 500 hertz, somewhere around there. We'll just say 300 hertz because that's normally about what these frequencies do. And we're going to talk about some of the complications that come with those higher frequencies later today. And obviously, most of the time, we are going to be working from 0 to that 50 to 60 hertz range. Anything else, you're probably working on something that's like some crazy high speed, like either a spindle or a centrifuge or something like that. And so normally we don't really work with those higher ends like up here. Normally we're working in this 50 to 60 hertz range. So that's what we talked about last week. We talked about different control modes. We talked about volts per hertz. We talked about vector. And we talked about servo control. Servo. And we also kind of talked about torque control. But we also said torque control, you want to try to avoid it unless you absolutely have to, because if you have a mechanical breakage, the motor can run away. Will run away. So that's an overview from last week. We talked about a lot more stuff. If you want to go through that, we had 3 hours of material on it. So we're not going to spend too much more time on that. What I wanted to talk about today was this is the structure that we have. So all of this is the structure of what a physical drive VFD does. We're going to talk about the electronic version, or not the electronic version of it, but kind of like what's going on behind the scenes, like on the electronics, that we as our drive engineers, our automation engineers, we need to take into account in order to actually make this motor act like we want to. Because ultimately, we're wanting to control an AC motor, and we're wanting to change the speed. We're wanting to, either it's going to be a conveyor belt, we're wanting to speed up, slow down, or part of something complicated like a robot arm. All of these things have our basic control structure that kind of has 3 embedded loops, and we're going to talk about control loops just really quick, and just kind of like a very much introduction to control theory. And if you've been into universities or anything like that and you've taken a controls class, there is a ton more stuff that whole classes, whole like systems of study that go around like how to control different things. Well, we're going to scrape just off the top of it, just enough so that you can specifically kind of get the idea in general of that you can generally get the idea of where to start controlling a motor with a VFD. So, no Netflix tonight? Well, hopefully you've already watched all of the good stuff on Netflix, and so now you're like expanding your mind instead of compressing it down with K-dramas and the new Rebel Moon movie or something. So let's talk about control modes, or not control modes, but control loops. So the general idea of control theory is that you have some variable that you are trying to control. Shocker, I know, it's crazy. And then you're going to have some system that is going to be an equation, okay? So, but this in general can be kind of a black box. And so this is going to be your output. And what you have is your set point coming in. So this is just controls 101. Very simple. You want to have trying to control an output, and you are sending into an equation or piece of hardware, whatever it is here, you are sending it a set point, and you're trying to get an output to control that. Now, that's the basic thing. Now, how do you know if your output is acting how you want it to? Well, you have something called feedback. And so when this would be what's on the screen right now, would be what's called open loop. And because there is no feedback, this person over here has no idea. He's just sending in a set point, and has no idea what's actually coming back. And he doesn't know if his output is going right or not. So in a very simple method, you could actually have a person sitting over here and watching the output. Okay, say that in a very simple control system, say we have a tank and we are wanting to control the level. Okay, and we have a pipe that has a valve here, and the water or the liquid kind of flows down in. Well, right now it's open loop. We turn it on. We have no idea if anything, how it's going. Welcome to the stream. Welcome to the stream. Wow, from India and stay in UAE. That's a pretty cool. I kind of pause, especially with the people that are chatting. I love having international crowd in here. I love seeing people from all over the world in different walks of life, and Siemens definitely does bring that together. And so, welcome to the stream and welcome to the community. Hopefully you find something that's useful in wherever you are in your automation journey. So talking back to our little control system here that's controlling this level, you could actually kind of have a person just sitting over here and looking down into the container here and say, okay, it's hit the correct level, and now we're going to turn this off and stop the flow, and it's at the correct level. So that would be kind of actually closing the loop. The person visually is closing the loop. Well, obviously that's not automated, and you could have a person sitting there making sure that tank is filled up all the time, opening and closing it, but we're trying to automate it, right? So we want to have some sort of feedback that comes back in and affects our set point, because we, in essence, if we want it to reach a certain level, we want that to say, hey, shut that off. So once it reaches a certain level, we want our feedback to come back and set the set point to 0. Well, now if there is a tank going out and it's pulling out, we can just say, okay, have a float switch that comes on and off, and like on, off. That float switch would be the feedback. Or we could have something like a laser sensor or something that's doing that we could then have a black box do some, call it black magic, some sort of equation that will affect the flow going out. Real simple, very kind of basic, intuitive process. So in a drive system, we are normally trying to either control the speed or position of our system, okay? And our motor is what is actually acting on that. So let's talk a little bit about the forces and the variables involved in this control system, because it's might not quite be intuitive if you're not used to them. So let's clear this out. What's up, everyone? More people from India. I love the fact that trying to get these streamed a little bit earlier in the day, it seems to be able to be where people in India and a little bit more in the Eastern Hemisphere is able to come in. So kind of been falling on this. Hopefully I have some US and Western Hemisphere people that are going on their lunch breaks maybe and could join in. But yeah, welcome to the stream. By the way, we have a Discord community that is free to everyone to join, and as you come in, you can join in and ask these questions. We have a couple different channels, some off-topic stuff to just talk about whatever, but then we have automation and then a help desk. And so even when I'm not on stream, I'm on that a lot. We use Discord at my company to actually communicate. And so If you have other questions, Discord's probably the best way to get in touch. But also, be sure to like and comment on this stream as you're watching it. If you're coming in with it on demand and you have a comment, you can comment in there. If you are live, you can like the stream and get it out there. We're probably going to be on live for at least a couple of hours today. So the more you like the stream while it's live, the more it gets out there to people, and the more people we get involved in the chat, and the more we could talk about these topics and cater them to you. So yeah. And kind of along that, if you're not subscribed to it, like subscriptions, you can turn on notifications to let you know when we do go live and when streams are scheduled. So that's another motivation to subscribe. So let's talk about these drive systems. So most of the time, let's draw just kind of out like a conveyor belt. And we can think about what we are trying to control. And so we have a motor down here that is attached to a shaft, some sort of coupling, and we have a box on this conveyor belt that we're trying to control. So we may want to move this box to a certain position. Okay? And so ultimately we are trying to control the position of our process. But in order to make that happen, we want to make the speed of this belt move from 0 speed, stand still, and then move, and then go to a position. Yeah, so Ignatius asks on chat if I'm a Siemens authorized drive certifier, because we'll need certification when you're done with the course. So one of the things, so I am certified in a lot of different certifications, S120 drive certification engineer. Was certified as like a TUV's functional safety expert. There's a lot of certifications that I have. One of the things that I am definitely looking at being able to do is figure out, especially for our members, a way to have certification tests so that you can get, in the US, the professional engineering degree, you need continuing education credits, and try to be able to offer those to you so that it has some sort of certification to what you are doing. In order to do that, I would need to be able to have some sort of feedback. But one of the things that I am going to try to figure out how to offer is some sort of, hey, here, you've gone through these tasks, some sort of certification so that you can put that out there. Okay, yeah, Ali Reza. We're definitely going to be talking about the motion control. So later on this week, since I'm actually in Atlanta all this week and I shouldn't be on the road, I'll be able to maybe do two automation streams this week, and one of them will be Motion 101, and I may go through some of the Portal 19 features that are available, because I use version 17 on what I've been using on the stream, and that's mainly so that in the memberships, when I make a file or make an archive, it's going to be in version 16 and version 17. Hopefully most everybody has upgraded up to that point, but I know that a lot of people are a few versions behind sometimes, so we'll definitely try to do that later on this week. So we're talking about this controlling the position of this box that's on this conveyor. Ultimately, we are controlling the conveyor, but in order to access that conveyor, we are controlling this motor. So the Delta picker is coming along. I probably am going to be doing some streams in the morning tomorrow, just working on some of it, or because Mondays and Tuesdays in the evenings, I do stuff in the evening that kind of take up all of my time. But then Wednesday, Thursday, and Fridays are the days that I actually kind of like dedicate to work. And at least on Wednesday, I'm probably going to be working on the Delta Picker in design. And so I showed this on the last stream, but if you're not, we're doing, I have the kind of interface coupling design that we did here, and we'll be expanding upon that, bringing this in, kind of designing in a failure point that I can replace, and so that's what this is for. So that's why we have the little key here. But yeah, Delta Picker project, if you're not familiar with what that is, check out some of the other live streams. We're going through, I definitely not for free, but I came, I ran into having some extra 1FL6 servo motors, which are for the V90 drives, and I had 3 of them, and so came up with a way that y'all could interact, and we're making a Delta Picker to control with a 1500T kinematics. So that's on the way. And we're doing that live on stream, and we're doing all of the different parts. Here's some 3D printing test parts, because behind this, definitely not fake wall here, is my Bamboo Labs 3D printer that is pretty sick and awesome. I love it. But yeah, so, and this kind of goes back to kind of talking about the Delta Picker. Ultimately, we are trying to automate an interface into the world, and this motor that is coupled up to some, in this case, it's going to be like an arm that's a part of a Delta Picker, and it's got all of these complex motions and all these different things ultimately come down to controlling the speed of a motor. Because ultimately, that's really everything that's going. You need to have that arm moving, or up on the screen right now, the conveyor moving at a certain speed at a certain point in time. So you want it to accelerate up, run for a certain speed for a certain amount of time, and then accelerate down, and then come to a stop. So if we plotted this graph, and this is 0, and this is the speed, so in RPM, this is time. This is what, if we wanted to move this box from here to here, kind of what it would look like. And maybe this is 200 RPM, something like that. And speed over time, the area underneath this curve is ultimately going to be our position, right? So we're controlling this speed, and if you're familiar with a little bit of calculus, maybe you're coming out of college, university, and you've taken a little bit of calculus, and these derivatives and integrals are kind of like the relationship between these equations, because while we have this sorry, gosh, I'm stumbling over this. While we ultimately are trying to control for position, we have a couple of different things that work together in order to control for that position. So that's position. As the speed changes, our position changes. Well, how do we change our speed? Well, we accelerate or decelerate. So how do we impart an acceleration or deceleration? We have torque. And again, if you've gone through physics, like a introduction or a calculus-based physics class, you know that there's these kind of calculus terms, the integral and derivative of things that go through. Now, you don't need to know calculus in order to be a good automation programmer and to be able to control a drive, control a motor. It just helps you to kind of really, it helps you more on the calculus side to understand, oh, hey, this is actually what this math is for. Because calculus was actually invented in order to describe physics, or at least Newtonian physics. So this sort of stuff. And that's what we work with for the most part. All that to say, I'm going to clear this out because we have kind of this understanding that we have 3 things that we're trying to tie together most of the time. If we're trying to control the position of something, we have to control the speed of the motor, and in order to control the speed of the motor, we have to control the acceleration of the motor. So why is that important? So if we are trying to control the position, by the way, if you're an engineer, it's okay to not be able to spell the most simple words like position. It's okay. It does not take away. Actually, I think it's a badge of honor to be horrible at spelling as an engineer. Just because I am. So we go from position, and what affects our position is the speed, and what affects speed is the acceleration, right? And again, we talked about for calculus that these are done by derivatives. So like a dx will move you up here. You take the derivative, you're going to get the acceleration, and there's actually a third derivative. And because the derivative is just the change in the delta. So the third derivative is jerk, and I'm not making this up. So if I call you a third derivative, you're a jerk. But the jerk is the change in acceleration. So if you go from 0 acceleration to a really high acceleration, we've all seen these like Ferrari videos or Koenigsegg videos where it's just like, ooh, we have like all this like acceleration, and you go from sitting, and then all of a sudden you're just like boom, and you get jerked back into your seat. That's jerk. That's the third derivative. So that's what we're dealing with. Well, in a control loop, you will have a control for all of these things. And so how do we affect the acceleration? What causes an acceleration on a motor? Well, on a motor, because it's rotary, it's going to be torque. So right? So torque is our variable, right? So that's what we are trying to control if we are trying to control an acceleration. We're trying to control the torque. And now you should start to kind of like, oh, hey, these are some terms that are definitely coming in and tying together. So if we are wanting to control the speed in a motor, normally that's going to be RPM. Okay, there are some, when we get into motion, we don't use RPM because we change kind of like what we're trying to control. But then in our position, we have some sort of length unit. Okay, it can be meters, it can be millimeters, it could be centimeters, it could be inches, it could be cubits or whatever. But in kind of like in Siemens world particularly, we just call these length units because it's some unit of length, and that's what our position is. And so as we move through these different controlling factors, we're going to use these different units. And so what a control system does is it starts to embed different black boxes, so functions, and then in order to control anything, we need to control this acceleration. And then to control this, we're going to need another function that kind of encompasses both of these, right? If we're wanting to control speed. And if we want to control position, it's going to need to encompass all of that. And so so we have these different functions that are controlling different levels. And you'll see that as we go from position, which in a lot of like motion systems, that's what we're looking at, position, we need to send out a speed set point. So This controller will generate an RPM value. So our position controller will generate an RPM value. A speed controller will generate a torque value. So every little nested control loop will send an output, will send a set point to the inner one. So the outermost one sends a set point of the value for a set point. So the output of the position controller is a speed set point. The output of the speed controller is a torque set point. And then the torque set point actually, that controller, the torque controller, actually outputs a current to the motor. And then that's where the true black magic comes in, and all of the stuff that you just kind of need to trust that it's going to work, because otherwise, why would you be using a drive? But so that's where we go. So we got so Ignatius is kind of talking about the drive certification as well. Talking about the safety incorporation. So if you are in a country that uses the CE mark, you're familiar with a safety certification for equipment. So functional safety. And one of the things that I was certified, the what's it called? The safety certification that I was able to have was TUV Functional Safety Expert, and we're definitely going to be having a class on functional safety, 100%, because I think that especially in the US, to where I say we're just starting. It's probably been 10 or 15 years to where it's the safety certification and the CE mark kind of, we don't require the CE mark, but the concepts of like performance levels and those things have really started kicking on. And there's a lot of things that if you don't do those things right, you can actually make the system more unsafe by implementing safety. So we're definitely going to have a class on that. Well, so got another chat. I really appreciate the compliments on this. I'm glad that these videos are able to help people, and apparently actually won a $10,000 competition in Dubai following some of the instructions. Now, that is flattering. That is very flattering. One of the things that like I always say, like, if y'all didn't know, I talk about my dad a significant amount on here, and just how he set me up for success in my life. My dad is probably at least a 150 IQ, very intelligent, but he grew up in a very rural, very like the absolute middle of nowhere. And so if you're familiar with the United States, just kind of like the southern US is kind of not known for its like ingenuity, but you get into these pockets and of places that like there's brilliance everywhere on the planet. There's brilliance, and my dad is one of those like absolute things. So he was able to teach me just whatever I needed, whatever I wanted to learn, like when I was growing up, and he was able to teach me these things. And so because I had that, it set me up so greatly in life. And that's what I'm just trying to do for you, because I know that there's a lot of people that are in those communities like my dad that maybe there's not a lot of resources for you. Well, it just like makes me really happy that something that I've said has been able to reach out to communities no matter where you are. And honestly, even in some of the really big communities, like here in Atlanta, we have some really good technical schools here in Atlanta. And sometimes if you're not involved in that community, you're kind of like sitting on the outside, and like you don't get the same resources, even if you're like right there. And so it really makes me happy that you've been able to get something out of this, because that's what the whole point of this is. So we're talking about these control loops, kind of getting back onto the topic of the drives themselves. We're going to talk about these different control loops in a drive, specifically trying to control our motors. And as you're going up, you might just be controlling a pump or a fan. Well, obviously, since you're not having to control for a position of a fan, there's no position in a fan blade. I mean, there is, but you're not, it doesn't matter. Like, what you are doing is you're trying to control the speed. You're not going to need the position controller. So you can kind of take in and out all of these values or these control loops as you kind of move along in your different processes. So a fan doesn't need position controller, but you absolutely, if you're going to do a delta picker, you absolutely have to control the position. So let's talk a little bit about Siemens drives, and really just drives in particular, because I'm going to be talking about Siemens drives, but they definitely, all of these concepts here, the torque controller, current controller, torque controller, speed controller, position controller, those are all concepts that are universal. So from here, I'm going to be working inside of Portal. I'm going to be working with SINAMICS. And if you're using SINAMICS, you're going to be able to duplicate exactly whatever I'm doing. Or if you're a member, you can just use the archive file for what we have. And you'll be able to go from there and work with it. Well, it's not just SINAMICS. It's not just Siemens. Especially the stuff that we're talking in probably the first half, probably two hours or so of this stream, is drive universal. This is stuff you're always going to have to deal with. So what I'm going to do now is kind of shift gears over into Portal. And just so that, like, if you're coming in, let me get swapped over. Where's my mouse? I have 4 screens here and kind of get lost. So let's get here and let's bring up Portal. And again, if you're not familiar with Portal, if this is your first time using Portal, I've got lots of other videos that are on here, live streams, edited videos that kind of help you in with this. And so this isn't really about necessarily the Portal specific, like, how-to stuff. And so I'm going to set up a brand new project here that is, I'm going to kind of just go through. And again, if you are a member, you will have access to this archive. And so whatever we do here today, you will be able to have access to if you're at the programming level. So I'm just going to go through like I normally do and add in for this. Let's just add in, since I'm not doing a anything really special, let's just go through and change to like a AC/DC relay here, and then a 40, because that's going to be the newest, and then we're going to call it PLC D102. We're going to add a new device, and it should bring up our device networks. And we're just going to disable all of this. These are all security. Obviously, you need to look at what those security settings are and need to make sure that you understand what you are enabling and disabling. One of the things that we use a lot in like PLC to PLC communication that makes things easy, if it's easy to do, it's probably not very secure. So one of the easiest ways to communicate PLC to PLC is using the put and get functionality. It's actually how like ignition works. Alan Bradley uses it in the in a lot of like HMI communication, and there's a lot of different things that it makes some security problems. So if you notice, I drug in a CU250S this time, because the CU250S has the built-in, I drug in the wrong one. I gotta have the Profinet version. Here, that one. Drug in the wrong one. I drug in the hardwired one. Wondering why it didn't have a assignment there. So let's do this. So drive. Oh, actually, that's cool. Do that. And then we're going to assign it to our PLC. And so that creates the Profinet connection. And then we're going to go here and we're going to set up a power unit. PM240-2. Let's do a 10 horsepower. Should be a or in this case a 7.5 kW. And so that would be a low overload, and we talked about the overloads are going to be I talk about those in depth in our industrial motor and drive sizing, which has been a couple weeks ago. There's a live stream that's really in depth about how to size your drives. One of the things that I brought up in that is that Siemens drives, the way that they rate their drives, so the low overload or light duty rating is actually thermally about double the thermal capacity of the way everybody else rates their drives. And so essentially comparing apples to apples for a Siemens drive, and this is the Siemens drive plug, the Siemens drive will be twice as thermally capable, and thermal, like heat is your enemy in a drive because heat builds up, it degrades components, it degrades IGBTs, it degrades capacitors. So if you go and do some of the worst applications, steel mills and coal mines, what I always say, you're probably going to see one of two drive manufacturers. That's Siemens and ABB. And they're both great drives. ABB has some really good electronics in it, but the ratings themselves, and again, watch that industrial motor and drive sizing. I go into why the difference is there, and it's on those duty cycles. So not all ratings are the same. So we got what G120 model has a Drive-Cliq network. So the 250S-2, so the one that we're using here, AliReza, the CU250S has a Drive-Cliq, and so Drive-Cliq, if you're not familiar with the kind of product portfolio for Siemens, Drive-Cliq is the communication protocol that it goes to the built-in motors on these on like normally in S120s, but this G120, which is the general purpose drive, the CU250S, not only does it have built-in encoder feedback, but it has a Drive-Cliq port. So when we go through and set up the motor for this, we can actually do a Drive-Cliq compatible motor, and we'll do that like in the actual thing, but we can actually use like a 1PH8 motor, because remember, while the G120 cannot do servo control, a 1PH8 motor, while it is in the motion control catalog, it is just a specially wound induction motor. And so you can actually run a 1PH8 motor in vector control because it's just an induction motor. It's not like this 1FL6 that's sitting over here. It is actually an induction motor. So what I want to show you is we're going to go into the drives, and we're going to go into the parameters for the G120, and we're talking about these control loops, and I want to show you kind of what I'm talking about from a functional standpoint in a G120, because we have our acceleration, which is torque. So I wanted to show you in our operating mode, we have our current controller, power module, and then, so this is our actual PWM. So you can see this is the controller that goes from, it goes from our set points from our current controller, which is, that's what this volts per hertz is. So it's setting our voltage and our frequency, and then it is actually controlling everything in order to produce the current that we need in order to get the torque set point. So a bunch of stuff here. We talked about this pulse frequency last week, and if you're not familiar with what that is, this has a lot of effects that we're going to be talking about later. Hopefully we'll have enough time at the end of the stream to talk about kind of like common problems that you have with a drive system. So if that's something that's interested, if you can hang around through the stream, do it. And if you're watching on demand, feel free to skip ahead because hopefully we'll have enough time to talk about the troubleshooting stuff. But pulse frequency can cause some problems. By default, that 4 kilohertz is on the smaller drives. Some of the larger drives, it has less. It has the 2.1 kilohertz or something like that. And by default, there are some other drive manufacturers that, because that 2 kilohertz, that 2 and 4 kilohertz, you can actually, I can't hear because I have hearing loss, but if you have young ears, you can actually hear that those pulses firing, and it kind of is annoying. So some manufacturers have said, oh, we're going to up our pulse frequency by default, and that causes problems. So we'll talk about that later. Yeah. So we have a commenter that talking about the G120X in Turkey, and yes, so the G120X is a version of the G120 that is specifically designed for pumps and fan applications. And when they came out with it, I guess it was probably 6 or 8 years ago now. I don't know, maybe not that long ago. But when they came out with that drive, it's less expensive overall because it has an integrated technology, where the G120, you have a separate power block, which is normally the thing that blows up in a lightning strike. Then you have all of the brains in a control unit, and so they call it the modular functionality. You can just pop the control unit off. You don't have to reprogram anything. You can change out the power block, pop that control unit back on, hook up the wires, and you're off. You're back running. So the G120 is really popular in the US because of that functionality. In other places where price point is a little more sensitive, I guess, then absolutely the G120X is going to be great for those drives. And we're going to talk about some functionality, some functions that are available in the G120, and you're 100% right in the fact that the G120X definitely has some additional features that are great just for pumps and fans, that if you're not using a PLC or you're using a fairly simple system, the G120X is great. And so, but there's some issues that, especially as a general performance drive, you can run into because of some of those ratings that I was talking about. For one thing, the G120X ratings are on a different rating system as the G120. Yes, there is also G120C, which is the G120 compact, and it takes away the modular functionality. It gives you all of the features of a regular modular G120, so like with the CU240E-2, and puts it all into one drive. The price point is a little bit lower. It's not quite as low as the G120X, but they are limited in their size range. So the G120C is only available up to, I think it might be like 25 horsepower or something like that. I can't remember which one it is because I think they expanded it. But the G120C, if you're down in a kind of 5 horsepower, 10 horsepower range, Oh, the G120C goes to 132 kW now. That's crazy. See, I learned stuff every day. So yeah, one thing also that the G120X has a higher like maximum power range. So the G120X goes up to I know it's at least 600 horsepower, maybe 700 horsepower, because I put a 600 horsepower G120X on a system here in the US. And the reason we went with that is because just the size range of it. The G120 modular, so just a regular G120 can only go up to 400 horsepower or low overload. So we're talking about this, our controllers, and kind of talking about the fact that ultimately the lowest level controller in everyone's drive, everyone's drive is going to have a torque controller, and it's going to be controlling the acceleration of the motor, because you can't control speed if you can't control up and down. So that's what this guy is here. And so let's just back through these control loops. And so this one is a standard drive control. So let's go through and change this, and let's see if we can do an expert. So I'm going to go back and go to commissioning on here and go to a commissioning wizard, and we're just going to kind of blow through this. So we're going to do expert. So all the options are available. Some of those things will limit the controllers, limit the options, and that's not what I want today. I'm going to turn on all of these things. Oh, I guess we can't have all of them. We don't need the position controller. We do want the free function blocks. We'll change all this stuff later, but we want speed control with encoder for right now. So let's go through, keep setting this up. Let's do a standard Telegram 3 because that has some. Yeah. Also on here, like these are your inputs, and you can select different I/O configurations, and we're going to talk about how you can change those later. But these are just standard I/O configurations that you can go through and check out. And this is what we're talking about in the US. We want to set this to 480 and 60 hertz line and freedom units. There's no bald eagle units on here. So we talked about last time about setting up braking resistor. Then on this, very simple. You just put in this value here in P219, set the maximum amount of power that you can output. So talked about that last time. We're going to talk about this motor side drive filter later. So motor configuration, let's just enter some motor data. I'm going to make some stuff up and see how close I am. So star, we're going to say it's 460. It's not a medium voltage motor. But, so we said this is 10 horsepower, right? So what that's going to be like 12.5 amps, something like that, 10 horsepower. We're going to go with about, we'll just say 90. And rate is 1750 RPM. That seems pretty good. Obviously, putting those in, you want to put the nameplate data. We're going to mess with this later. So I'm going to enable that. Reference speed is 1800. 2000 maximum speed, ramp up time. We'll talk about that later. And our standard drive. So I actually learned some stuff. This application class has to do with some standard communication profiles that, because I use so much Siemens, that I didn't even realize that was what that was. That's like a Profi drive standard communication that's across manufacturers. So If you put standard drive, then it just kind of opens you up to whatever. And we'll talk about this here in a second, but this complete calculation takes all of those numbers and fills out the motor model, the basic motor model. Talked about that in Drives 101. So if you're not sure about that, then probably need to check out the last week's live stream. So this is our encoder. We'll just call it a 1024 TTL, or I guess that's a HTL. So HTL AB, that's pretty standard, and it's going to come from the terminal list, or sorry, the terminal interface on the CU250S-2. Also, we're kind of talking about the different motor types. Currently the only encoder interface is going to be either on the G120, so the modular, or the G120D, which is the distributed drive, which I don't even think I've ever talked about, but you can actually put that out. It's an IP67 rated drive that you could put out on like a system. Maybe it's not. Maybe it's IP65. I don't know. It's meant to be out on the thing. That's the G120D. Conveyors mostly very similar. If you were, I think it's the SEW Euro Drive. I think it's the Movi Fit series. Correct me if I'm wrong on that one. I think it's the Movi series that's intended to be out on the conveyor itself. That's very similar to the G120D distributed. Those are the only two options for encoder. So we got that. We went through the commissioning wizard. It's set that. We're going to save that. And now we're going to go here to go back to our parameter set, because now we have a couple of other things in here, and that's why I wanted to. So we have our current controller, because before, when we didn't have all this set up, it didn't have all this stuff. So one of the things that we could see is that ultimately coming out, we are going to have some sort of like current set point that's coming out, and our pulse with our PWM controller is going to be actually pulsing all of that inverter bridge that we talked about. It's pulsing all of that to create that kind of variable signal. And again, we talked about that in Drives 101 of how it actually does that. That's something pretty important if you missed it. So let's go back to our torque set points. Okay, so ultimately we talked about the fact that we're in let's just talk about a fan right now, or a pump. We're going to send out a speed set point. So ultimately you need to have the torque of that motor is being controlled. So that's the innermost loop. And honestly, you probably don't ever really mess with that, especially on an AC motor, because there's a lot going on there that you don't really need to mess with, and you don't really need to tune, because an induction motor, you can't really tune most of that. Now with a DC motor, it's kind of a little different. The torque controller, the current controller actually needs to be tuned for the motor. You need to go out and look that up and see that. But on an AC motor, the tuning process is built into, sometimes in the US they call it a wake and shake. Here it was that drive or motor identification at standstill in the wizard, but we're going to go through that here in a second. So ultimately, we're trying to output this current and torque. See, we follow through all the way through, and we are outputting a torque value that goes into our current controller. So our control mode that we are using, though, is speed control with encoder. And I'm probably going to move this down onto the other screen here for a second, but because I want to be able to kind of highlight some stuff. So give me a second. Let me put you here. You get to look at me full screen. Aren't you happy? Let me pull this down onto this other screen here. Clear this out and fix that, because that is not what I was wanting. And we're going to come back down onto our sketch pad. So now what we have here is to where I can draw on the screen. And so what we're looking at here is, if you notice, this is output is in Newton meters. So that is our torque output. Well, before we talked about kind of our output having a feedback coming back, and then set point, and this is our feedback, and this is our output, right? This is kind of what we were looking at. And then we have some sort of function in here, okay? And in this case, we can actually see that. So we are outputting from our speed controller, we are outputting Newton meters. So what our feedback is, the units it is in RPM, because we're just doing a subtraction here. And we're creating here what's called the error. Error. It's one of those words that my southern mouth just can't really completely form. So it's error. We talked about that today. And so that signal right here, that's the error. And then this is our set point. Now, it obviously has a bunch of other stuff that we may talk about here in a second. So this is our set point. This is our error. This is our output. And this is our feedback. Okay, so that is our speed controller, speed control loop. So our set point is speed. We are trying to control speed, but the output of any controller is always going to be the derivative of that controller. So we talked about that before. You don't need to know it, but just know that the output of the speed controller is going to be torque. The output of a position controller is going to be its derivative, which is going to be speed. So it's the change. The change in position is speed. The change in speed is governed by torque, which is acceleration. So that's what we have here. We have a couple of other things in here that are kind of important that we're going to talk about how to actually tune this here in a second. Because we have these factors here, right? We have these numbers here. And if you notice in my little scribbled down drawing down here, down at the bottom, this isn't here because this comes back as RPM is our feedback, because this is in Newton meters, right? Well, in this, we have some sort of function here that is the actual controller. Well, for this is really just a PI controller for the speed. And this is something that you might have some familiar with, is the fact that like you have a PID controller for like on a pump to where you're controlling for pressure. Well, same concept, except all of these are just built into this drive so that it is controlling the, it's a PI controller controlling this output, which is torque. So one of the biggest things that you have to do is set these PI factors in order to make it to where it controls the motor, it controls the speed properly. We're going to talk about that here in a second. So here we have kind of this setup. And so that's in general what you're going to have for every drive is going to be a speed controller that is going to be outputting a torque. And that's really what we get out of this. So ultimately, that's going to output that. And so let's clear this out and then click through and go back a little bit. And you can kind of see that there are some set points to where we can put our set point into these drives in different places. Normally, you're going to be putting in your main speed set point, and then you're going to be taking using a ramp function generator that's in the drive, and that's kind of like set up here. And you can set up all these things. Before in our thing, we have some sort of ramp up, ramp down time. So if we want it to ramp up faster, have a faster acceleration, we could set it there. If we want it to ramp down faster, we can set it there. But remember we talked about last week, slowing down an induction motor pumps energy back into the drive. And if you don't have a way to deal with that energy, things can go boom in a very dramatic fashion. So slowing down a drive breaks a drive. So it puts the brakes on. And if you're doing active braking with your motor, with your drive, just by slowing down or speeding up the deceleration, so making that value, pumps more energy back into the drive. So normally you want the ramp down time set as low as possible, because that's gonna generate the least amount of waste energy. So we'll talk about that here in a second, probably a little bit more when we talk about the VDC Max controller, because there's a lot of other controllers and a lot of other functions that these drives have. We're just talking about the basic functions. So I don't know, I don't have the ePause turned on this, so the position controller is not turned on. But what would happen would be this ramp function here, kind of this ramp function, you will take and put in a set point of like 1000 RPM. And what a ramp function does is, instead of just going from 0 RPM to 1000, instead of doing that, it will take and smooth this function out over some sort of time period. All right? And that's what this ramp function does. So what comes from your PLC is 1000. What your actual controller sees is right here. It slowly increases. Like that. And so that can cause problems, because if you have some sort of controller on your PLC and it's doing math and it's looking for this thing to change quickly, and it's not changing quickly, it's going to say, hey, it might have a PID controller, especially if you're using like a speed set point, a position set point. So if you're using position controller, like on the technology object, if you're using a PLC based position controller, then having a ramp function on the drive is going to cause an incredible amount of problems. Your system is not going to be able to work if you are using a ramp function and a PLC. The input, the set point from the position controller in the PLC is coming through that ramp function. It's just going to cause all sorts of problems. So what happens on this is that's why you have, here's the path from the ramp function generator. Well, this is coming in and setting a set point in here, and this is where like a position controller would input its speed set point. And so it would come in here and get put in, because you don't want that ramp function interfering with your speed set point. That's if you're using a position controller. Now, if you're not using a position controller, this is what you want, because you don't want that motor trying to just like 100% torque, just boom, like going, it'll break couplings, it'll do all sorts of stuff. And most position controllers have some sort of like, okay, I want to slowly accelerate. And so it's controlling that ramp in there. Whereas if you don't have that functionality, you want to use this ramp function. So we have the three different things. And for this, we have speed, speeds, torque controller. All right, and so that's pretty basic. Now, what I want to talk about now is how do we actually kind of set, or kind of like, well, we're going to talk about here in a second how we set some of those values and kind of like where we start. But I want to talk about some other functions that are available on some of these drives, or at least on, I guess, some common functions that are available on drives. We talked about one last week. And it was called the VDC Max controller. And I'm going to reiterate what this VDC Max controller is. So if we talked about that motor being out here, it's connected to the inverter bridge, and then it has this DC link, right? So these are big capacitors. Well, if you try to slow down this motor, so like we were talking about before, if you're trying to brake, decelerate this motor, normally when you are motoring, the current flows out to the motor. Well, when you are braking, because of reasons we talked about last week in depth about the motor torque curve and slip frequencies and all of that stuff, check that out if you don't know what I'm talking about. But because of that difference in rotor speed and field hertz, so like the line frequency and the rotor frequency, because of that difference, this current flows up into the drive, and it's going to flow into these capacitors. And so if you have your DC link voltage maybe normally at 650 volts, yeah, so there's a chat talking about the active line module. I think it was 2 weeks ago, I actually did a whole stream about the active line module, and these are some of the things that we definitely talked about. No, the active line module is a very good rectifier. Most drives do not have the performance of the active line module. And in the active line module, it is what's called a regenerative rectifier. And it puts this energy that we're talking about here all the way back onto the line. The thing about it is no matter what rectifier system you're using, this concept is going to happen. Your DC link voltage is going to, the energy is going to come back in from the motor into this DC link. And so this concept is based on the motor. What you do with this energy, so like if we're going along and the DC link voltage is at 650 volts, well, say the one of the things that is better, or traditionally better, about Siemens drives is the capacity, the voltage rating on their capacitors. Say that they are rated at 1000 volts. I mean, I actually don't know what they are, but as you start pumping this energy from the motor, because you're trying to decelerate this thing quickly, you're putting this energy back into the these DC link capacitors. And if you don't do anything with them, they will go up and up and up and up and up like that. As long as you're braking, that current's coming back in, the voltage is going to go up. And obviously, if you have 800 or 1000 volt rated capacitors and it keeps going, it goes up to boom. And I don't know if y'all have ever been working on a little capacitor and you accidentally put too much voltage on like a little capacitor on a circuit board, a very small capacitor will make you jump really high. Well, these capacitors in some of these drives are big and there's lots of them. And so when some of these drives go boom, they go boom throughout the room. So needless to say, this uncontrolled rise in the DC link voltage can cause major problems, and you don't want that to happen. So what the VDC Max controller is it says, hey, if I have a switch on level, okay, I have this switch on level here to where, say the switch on level is 800 volts. At 800 volts, it is going to limit the amount of braking torque out to the motor in order for this DC link voltage to not build up anymore. So in essence, braking torque is decelerating the motor, right? It's coming down. If you decrease the braking torque, so you start to lower the negative torque, then essentially what you are doing is making the motor slow down slower. So the rate of change in the motor speed is lower. So essentially you are extending the ramp function. Instead of having a 5-second ramp, it says, hey, I can't do this. I can't do this in 5 seconds. It's going to take 7 seconds. And the way it does this is just simply by limiting the braking torque. So it starts to lower it so that this hopefully will do this and level out and then come back down. Okay? And that way it does not go boom. Well, let's clear this out and kind of look at some of these values here. It's pretty simple. It's a pretty simple process. You have the switch on level that we talked about, and then you have the dynamic factor. Really, honestly, you want this to be 100, and we can click on here, clear, and you see that there's some settings and everything, but most of these are always going to be set by the line conditions, the motor conditions, like those sorts of things, and they're set in real time. So we have someone in chat that's asking if we in essence it's limiting the output current. And so the sign of, so like the output current, if the current has a positive sign, so if it's like 100 amps of current, that means it is motoring. If the current has a negative sign, that means it's braking. That means because it's negative, it means it's coming back into the DC link. And so that is called a generating. Because it is acting like a generator, like you would see at a power plant, like a steam mill, a hydroelectric, a windmill, something like that. It's actually generating power. And so all this does is, in essence, puts a negative cap. So if negative 100 amps has moved this value, or negative 100 amps is causing the DC link voltage to really boost up and go too high, it will move it to negative 90. If that still is going too high, because there's a PID controller in there, if it's still too high, it'll move it to negative 70. Whatever it takes to keep that DC link voltage from faulting out. Because ultimately, if you hit a fault voltage, which I think on these by default are like 830 or something volts for a 480 volt line. if it hits that, it faults out and it just stops and lets it go. And you don't want that to happen for a lot of reasons, but you never really want to be faulting out your drive, because at that point that load is going to be doing whatever, like it's not really controlled. So this is just going to lower the negative torque limit, negative current limit, until just to try to prevent the drive from faulting out. So yeah, and you can also, we're going to talk about that here in a second, but I'll show it to you here. Clear this. Here in torque limitation, you have two sides. So you have your you have your positive. So these are all your positive torque limits. And then you have your negatives. So all of these kind of like positive and negatives, they don't have to be the same. And sometimes if you cannot handle any if you cannot handle any braking current, say you have very little resistance in that DC bus, you can't get any DC link voltage, you can't bleed any of it off, you might want to set this negative torque limit to 0, or something very, very small, something that's just barely enough to be able to do that. Because again, the worst thing you could do is fault the drive out. No, actually that's the second worst thing you do. Worst thing you could do is blow the drive up. Second worst thing is to fault it out. So you might want to set this, while this motoring could be like 1,000 Newton meters, and then this you only want 0.01 Newton meters. Now, essentially 0. So there's reasons for you to do that, and the VDC controller, the VDC Max controller, all it's doing is essentially controlling this overall set point. So it's just controlling that negative set point. It's automatically setting it. And you kind of have to have this control in some way on a drive, because otherwise, if you don't, your drives are just going to blow up all the time, because it's really hard to prevent that negative current, because even you can generate a negative current spike just by not tuning the motor properly, because you can overspeed that motor, and then your PI, like the speed controller, is like, oh nope, I got to slow down a little bit, and you're not changing the set point at all. It's just you tune the PID, you've tuned the speed controller too hot, and so it's very hard to prevent 100% of these values coming back in. So whatever drive manufacturer you're using on Siemens, so the question in chat is, the drive would blow up basically if we don't have a braking resistor. So if you have a braking resistor, you don't necessarily need this. You don't need this controller. But I will say, you can set that switch in level. If you set this switch in level below the switch in level for the braking resistor, then this controller will kind of kick in, and you'll never break any energy out into the braking resistor. So you would want to set it up to where those are flipped, to where your braking resistor comes on and breaks off any energy, because you want to be able to go quickly. You want to be able to brake and decelerate fast. But in the event of, hey, maybe you're braking too fast for that resistor, and the chopper can only chop out so many kW, and for some reason something's going on that voltage continues to build up, you would want to have kind of an extra level of protection before you fault it out or blow up the drive. Now, Siemens drives, 99 times out of 100, unless you have done something really wrong with your mechanical system, they're not going to blow up. Even if you don't have this VDC Max controller on, they're going to fault, and then whatever mechanically you have set up to be able to actually control it is going to have to come in and catch it. Like, this is where, like, you could kind of use this as like a process prevention. The drive is going to prevent, or is going to protect itself. At least Siemens drives, in my kind of experience, it's hard to blow up a Siemens drive. The only time that I have seen, or there's two reasons why I see Siemens drives blow up. One is because of lightning strikes. You can't stop lightning from blowing stuff up, like, just plain and simple. And two is because you didn't form the capacitors, which is something that is kind of an advanced topic that has to do with the capacitors. Like, if you sit them without voltage on the drive for a long time, and that's a byproduct of the capacitors, the dielectric construction of the capacitor. That has nothing to do with Siemens. In my experience, Siemens does a really good job of protecting the drive. Now, if you don't turn these features on, you may be faulting out. And say, for example, in an extreme example, but one that you should know, if you have like a crane or a hoist, where you have some load that's suspended, and you're holding torque in order to keep this load. Well, if you overload that motor somehow, maybe like drop a load onto that, like something drops and you have this big impact, well, it's breaking that, and so it's going to put braking energy back into it. Well, in that sort of situation, what would happen is this situation would end up being like a with the VDC Max controller. If you didn't have some sort of mechanical brake to catch that, and you didn't have enough electronic braking, the VDC Max controller would be like, oh, I can't take all of that out. So your load might sag, so it might go like sag down like that. Or if it's a really heavy overload situation, it might just completely slowly drop the motor, because it can only break out so much torque. So in that case, though, what happens if the drive faults? Well, if the drive faults out and you don't have this, then the brake on your load, hopefully you have a good enough brake, the brake is going to have to come in and catch it quick enough in order before that, because otherwise that can like drop really fast. So that's kind of what this VDC Max controller is for, is kind of like to try and prevent it from actually faulting out. So we've got a question about, is there a group that specializes in Siemens so I can study? Well, you have found the group. We have a bunch of videos here, a bunch of live streams, and if you comment what you would like to see, I try to integrate that into the stuff. We have a Discord server that is available for you that you can join for free and kind of ask questions with other automation engineers and kind of like guys with more experience. So that's probably a really good way. And if you are wanting some of the stuff, kind of the files and stuff that we are working on, there are membership levels that you can join into this community to get these files so that you can go through and dig through on your own. So that would be also a good way to study. Also have another shameless plug, y'all, those that are around, my dad and I have written a couple of books. The first one, which is on AC drives and motors, has a lot of information that is about got some of that. So so on the Discord fault, there's a couple of things. Try using a VPN from like a US based server if you're having trouble with Discord. Sometimes Discord will limit traffic based on IPs and stuff like that, and that may be an issue, because we definitely have had some people that are joining from kind of all over the globe, and so there might be some issues just with that. So if you have a VPN, to try to use it, because that might be an issue there. But yeah, so with that said, we're talking about the VDC Max controller. So we kind of understand that, and it's a fairly simple concept, but it's just kind of this upper level, like, hey, we're going to limit the negative torque that is available in order to protect the drive. So next thing I wanted to talk about was the what's called flying restart. Okay, so flying restart is something that you may not think about that being a problem. So one of the problems with these drive systems, or sorry, with a motor system, say you have a large high inertia load, say you have some sort of flywheel or a big fan, and so you have a big fan out here like this that has a lot of inertia. So it spins up, it's on really good bearings, and something happens, don't know what it is, but the drive faults out, or power goes out and it's sitting there spinning, and it takes 20 minutes for this thing, the resistance, to slow down, and like to slow it down to a stop. So, or maybe some of these things like flywheels, like on presses and stuff like that, sometimes they take an hour to be able to slow down. So obviously, if you have some sort of power failure or something like that that causes the drive to fault out, communications failure, something like that, you have this load that's sitting there spinning. Well, if you just go and try to say, hey, I'm going to start up this drive, talked about the difference between the rotor speed and the actual drive, the line frequency, that if you were to output and turn on your drive, by default that drive is going to come on and it's going to start pulsing out at a 0 hertz signal, in essence. So you're going to have whatever speed is out there, and you're going to have this incredibly high negative current spike. So all of a sudden, all this energy is just going to shoot right back into the drive. Obviously, we just talked about this. The VDC Max controller, that's a problem. High negative current loads coming back into a drive is going to be a problem, because, and so you might say, okay, well, I'm just going to figure out, and instead of starting it up at 0, I'm going to start it off, instead of starting it out at 0, I'm just going to figure out what speed it's turning at, and I'm just going to set it to whatever that is, and then start it up. Yeah, kinda. And that's kind of what will be good. It's got a couple. Hey everybody that's coming into chat. So if you're coming into chat for the first time, be sure to drop a hey, where you're from, and just like welcome to the community. We've got some other questions. We're talking about this negative torque limit, and so yeah. So the question is, if you understand this correctly, the negative torque limit is the max braking over some time for the motor. So yes, the negative torque limit will limit how much braking power you have. And if you're familiar with like cars and like F1 and all these different things, there used to be a system called the KERS system, to where as you would brake throughout the lap, you'd build up this energy that you could use for the KERS system. And this is that same concept. And yeah, it's the same sort of thing that's there. You limit the amount of current that can go out with the positive limit, and then you limit the amount that can come back in with the negative limit. And so that is absolutely the amount of braking power. And remember, I showed you on the little braking resistor set point. That's just how much power can be braked out to that resistor, and that is based on the physical construction of the resistor. And so that's how that works. Same concept. Negative torque limit is the amount of braking power you have available in your drive. And just because you set it to have 100 Newton meters of braking power does not mean that your drive can handle it. If you have an active line module, it absolutely can handle it. Cool thing about the way Siemens rates their drives, their regen drives, is their motoring rating is the same as their generating rating. So everything is rated both ways. So if you have 100 kW rating on your drive, that's motoring rating. You'll have 100 kW generating rating, and it won't care. So we have got, so we're talking about this concept to where this load is spinning. And so this is called the flying restart. Flying restart is a system that goes out and automatically detects in vector control. It says, hey, I'm going to barely put out just a tiny little bit of current out there just so that I can tell the speed that this thing is turning at. And so we talked about the vector model last week in the 101 class, in that it's looking at what voltage is output and what current feedback. And so it will just put out just an ever so slight bit of voltage, and it will detect that vector algorithm. And so it'll detect that vector. And so it can tell, oh, hey, this is spinning at 100 RPM. And then it will go through and then set the drive up to where it catches it. And then what you do with that at that point is up to you, because it's now catches it, flying restart, it's running, and then now it can start to control the motor according to the ramp. If you don't do that, things can get bad very quickly. And if you switch a drive on and it's on a motor like a flywheel or something with a lot of inertia, or a fan with a lot of inertia, then you're gonna have a bad time. So one of the things that the settings that this motor magnetizing current, that is detected automatically. So this is detect, CE detected, detect. Anyway, so I don't need that T. Again, spelling is optional. So detected with standstill measurement. Okay, so these are two functions that are very valuable. They are very kind of like critical to keeping your drive alive. So VDC Max controller and flying restart. And so this knows the motor magnetizing current. And so it's going to put out, say that's 50 amps. On a large motor, that's probably pretty reasonable. Say it's 50 amps. So it's going to put out 50.1 amps and going to detect what happens in the motor. And so it kind of sends this pulse out. And so this kind of goes through here, kind of the stages. So this is demagnetized. So that's where it connects everything up and demagnetizes it. And then it sends out this little pulse in order to find the speed, and then it magnetizes up the motor, and then it actually does the ramp up. This is according to the speed set point, and then now you are running back at your set point. So that is a flying restart. And if you have a big fan or a big flywheel or something like that, you need to use that motor. Also, if you have a load that like in a multi-stage pump, for example, you have a pump here, you have a pump here, and they're connected, so the water is coming in like this. Well, if this pump fails, or power spikes or something, if it faults out, this turbine is going to be being driven by this pump, right? So this pump did not fail, and this one did. And so that pump is going to be driving that fan. Well, if you try to start this up without a flying restart, at best, it's going to fault out every time. Just every time it's going to fault out, overcurrent, overcurrent, overcurrent. And so at worst, it's going to fault out with a big bang. So you don't have to have a big load. If you have something that causes that your motor to run without input, you need to use the flying restart. So clear that, go here. We're going to talk about the next thing. So those talked about, I'll go through brake control real quick. So you have a motor holding brake, and I want to talk about the motor holding brake because it is kind of the most important things on it are going to be these two values here. These are the brake opening time and the brake closing time. 100 milliseconds for anything but a very small brake is going to be too short, because what this does, the brake opening time, is the brake opening time, the motor, the drive will magnetize the motor and then wait the brake opening time. Sorry, got that backwards. It is going to build up the torque in the motor, and then before it actually starts to go and drive off and actually output the torque, the full torque, it will wait this opening time. So this is the open time. Okay. The brake closing time, say the drive, your speed is running, it's going to go down to 0, and you want eventually for it to demagnetize the motor, right? You're not wanting to hold torque. So like on an off 1, you enable a drive, you go, and then it goes off. Well, it goes to 0 speed, and you get the 0 speed detection, and then it's going to demagnetize the motor. Well, this brake closing time is the time between when it hits 0 speed and when it demagnetizes the motor. So kind of the STO type sort of thing. So those are two very important things, because if you have a load that you're actually using that holding brake, you don't want it to yes, yeah. So there's a comment about the magnetizing time in in cranes and hoists, because in those big motors, to magnetize those motors, it takes a really long time, and so you're kind of increasing that time before you're opening up that brake, and so that's what these brake opening times and the but if you're watching if you're getting a lot of information, new information out of this class, you probably need to be working with someone else if you're doing a crane or hoisting application. I'll put it that way. They are very dangerous, and there's a lot of things that you need to have experience on in cranes and hoists that if you're running a conveyor and you get these things wrong, it's not too big of a deal. But there's a lot of like problems that cranes and hoisting applications, like this magnetizing, demagnetizing time, that you're like, what in the world is that? That is incredibly important to know in a crane application. And so that's why you have these kind of apprenticeships, to where you have people that are experts out in the field and you work with them. And so these classes are definitely helpful, but they are no replacement for experience. I have 20 years of experience in this sort of stuff, and so that's why I'm comfortable with being able to do that. And there are some applications still that, because of my experience, I understand that, hey, I need to have other people checking me on these things. So as an engineer, and this is just kind of a word of advice, put your ego on the shelf. If you want to be a good engineer, always understand that you can learn from anyone, and especially always assume that there is something that you don't understand in an application that could have catastrophic like problems with it. When I was at the coal mines where I first started working. Now, when I started working at the coal mines out of college, I already had 8 years of experience in automation, just because my dad owned an integrator outfit, and so I worked with him on his jobs. All that to say, they had these 30-ton skips where they're pulling 30 tons of material a time out of the ground, and our mines were about 2,000 feet deep. So what is that? Not quite 1,000 meters, but 2,000 feet deep or so. And we were running at, I want to say it was like a minute a cycle. So we were running at, or it was a minute and a half a cycle. Incredibly fast speeds on these 3,000 horsepower motors. So very, very fast, very heavy. And in making these changes, one problem, like with a demagnetizing problem, if that brake does not close and that motor demagnetizes, by the way, we would never demagnetize those motors, but if that brake were to close and that motor was demagnetized before that brake closed, it would cause a problem to where there could be slippage, and then when it closed, the ropes on the bull wheel would actually slip. And there was an instance, definitely not when I was there, but at one of these mines with a very similar thing, to where they were pulling an overweight load, and the friction on the ropes were at the very edge, and it hit the top and it shifted just a little bit. And they were pulling this load because it was wet material. There was a lot of water that had gotten into it, and so it increased the density of the coal in the skip. And when it got up to the top, it wasn't quite right on the drive, and it went bump, just a little bit of shift, and that little bit of inertia changed it from static friction to sliding friction. And that was it. That was all it took. And fortunately, they were able to yell down to the people in the bottom to evacuate the bottom, and it about 90 seconds later, the entire bottom of that shaft with that 35 tons just went out. No one was injured, miraculously, but the entire mine was shut down for a year because of this, because that was the production. So the worst case would have been someone lost their life, but that incident was just because of a little bit of a shift, and it caused hundreds of millions of dollars in damages and losses, and very easily could have been a loss of life. So I say that to where drive systems, when you're learning about them, be humble. Be very humble. You're not turning on and off lights, you're actually moving stuff. And when things move, things can hurt people, things can injure people, like you can damage equipment. So not meaning to be discouraging, but that's also why it drives people. So what you're hopefully striving to be, once you have that experience, you will always have your work and your experience be in demand. You will always. So strive to be these difficult things, but stay humble. So thank you for bringing up that fact about like the cranes and hoisting, because that is very, very important about all this stuff. So let's talk about, because we are at 2 hours, and that's kind of crazy. I thought I was gonna have to like stretch in order to get through all, to kind of get 2 hours of material out of this, because I want to talk about a little bit about tuning, and we're going to kind of go through just real quick about tuning a speed controller, and kind of this will be from kind of an intuitive standpoint, not the math standpoint. We've talked about this before, like with PID controllers, that there are some math-based methods. We have a commenter that's on the stream a good bit that he kind of brings up. He kind of brought up the last time we talked about this, some interesting math-based methods of tuning. Well, we're going to introduce kind of the basic concepts as we bring up the speed controller and what it actually does. So we've talked before about what in a PID controller, when we've talked about like the PID simple blocks, and you can kind of go back and look at those blocks if you want to, but just in general, what you want to do is you want to set up a trace to trace the speed set point. Let's see. Let me get this. You want to trace the speed set point and then the speed actual value. And you want to set those up on the same graph. And in a perfect world, what you would like to do is you would like to create the set point to do this. It's called a step signal. And so you want to go from some value, say 100 RPM, to 200 RPM. And you notice I'm not going from like 0 to 1000, because if you're doing a 0 to 1000 set point, there's all sorts of stuff that like can come into an effect. You want to have the that's awesome. Yeah, hopefully even if you're just wanting to like go to sleep tonight and get some nice rest, you can just leave this stream on, or you're watching it on demand, and it'll put you right to sleep. Hopefully my voice is soothing to your ears. But the soothing qualities of a PID controller, see how I transitioned from that, can be kind of hard to get to. Give yourself the advantage, pick some value and get it like 100 RPM, something that you're comfortable with, that it can just kind of run at for a while, and then bump it up to something that it can easily accelerate quickly to. Because what you want is you want to have the set point to be able to go just like straight up. And then to give your motor the most chance at success of being able to actually trace that. And so that's why you just take 100 to 200 or maybe 300 or 400, but you don't want to go from like 0 to 1000. Always have it to where it's sitting there running at some speed if possible, and then have it jump up to say 10-20% of the total range of it. So what will happen is you will see the actual value. So this is the set point. So the actual value, can I get another, hold on, let me see if I can get another color on here. I can. So And what you will see is the actual value will be kind of sitting around like this, and then it will try to react. Okay? And it will look something like this. Okay? Now, what you are trying to kind of control for is how fast it gets to the set point. Ultimately, I mean, you're really trying to balance two things. Most people say, I want to get to the set point as fast as possible without damaging my system or wearing out my system too quickly. Most of the time, if you don't have slop in your system, you can accelerate and decelerate pretty quickly. And so it's okay. It's okay that this black line is pretty steep. It's okay to have overshoot most of the time. There's some cases where you don't want to have overshoot. Those are pretty few and far between. But in general, what you would like to do would be to have this go up fairly quickly, overshoot, and then come and settle like this. Okay? So the first case is if you have your P gain factor is too low. Your value will look something like this. It will be sitting down here, and then it will do something like that. If your P gain value is way too low, that's how it's going to look. That's called an underdamped system. There's not enough gain. If you never overshoot on a drive system, you probably don't have enough gain in it. There's probably some reasons why you would never overshoot, but in general, you want to have a little bit of overshoot because that means you're accelerating to that set point fairly quickly. Now, there are cases to where you can get too much gain. And what will happen there is you'll be sitting here and it will go up and it will resonate continually. And you'll hear this because what it'll be like a tuning fork. And it'll go, ooh. Sorry for your ears. I just wanted to like make sure that you understood that if you get your gain too high, your motor will sing. It will actually make a high pitch squeal. If you hear that, stop it like quickly. You've gone too far. But you kind of know your limit at that point. There are auto-tuning functions that sometimes, if you don't have a lot of inertia in your system, they will set the gain really high. And when you actually go to run it, it'll make that just like randomly. You'll stop it, and then all of a sudden it's like, and like making that noise. So what you want to do in general, you want to increase the gain from default, which when you do this, if you enable this kind of speed optimization, that's going to go through and do a rotating auto tune, and it'll get it pretty stinking close because it's going to do these kind of like jumps up and down, up and down, up and down. But if you can't just run it indefinitely and you can't go at all the speeds, maybe you don't want to do that speed optimization. But what you in general want to do is you want to go and increase the gain to where you have some sort of overshoot. And once you get to that, you know that you want to try to set like an upper limit on the gain. And so you want to increase it to where it starts to sing, but just barely. And then you're going to back it down. Okay. So you want to find your upper limit and you say, okay, that is as high as the gain ever needs to be. I never need to go that high and then bring it back down. And so what you will have is this kind of like ripple effect that I have here, right? Once you've backed it down, it'll have too much ripple. And so what you would really want is to pull kind of these ripples back. And the way you do that is by lowering this integrator time. And I've kind of like blocked it off up there. Let me see if I can erase some of that. There you go. So you want to lower that integrator time. And so that integrator time is essentially taking all of this this error that's here underneath the curve. And if you've taken calculus, you know an integrator is calculating underneath the curve, and it's trying to correct for that. And the lower this value, the faster it is going to try and correct for that. So the bigger the effect is. So if you want to take out an integrator, just put it at some really big number, and it's not going to have really any effect, because it's going to be such a small value, because it's not really technically trying to correct for that the area under the curve. So the closer you get to zero, the more. So 20 milliseconds is a very high integral time. Okay, so normally I find that it's around like 30 to 75 milliseconds is usually pretty good. But what you want to do is set the gain to where it's not resonating, and then lower your integral time to where it kind of makes it stable and it settles out. The higher the integral, or sorry, when you hit that sweet spot, this this area under the curve, it'll shoot up, but then it will settle much quicker when you have the correct integral time. And that's in general how you want to do it, because in system you have a lot of things affecting it. Like a conveyor, you have spring rates, and if it's a rubber conveyor belt, there's like springs and stuff that can complicate things. But in general, you want the gain as low as possible in order to get the performance that you need, because but you want to know what that upper limit is. And so the gain is kind of how fast it shoots up. It's okay to overshoot. In most drive systems, it's okay to overshoot, and then the integrator time will settle it out very quickly. So that's what these are. So we'll probably do a whole class on tuning, but that's just kind of the introduction to the basics of speed controller tuning, because a lot of people are like, well, I don't want to overshoot. Well, if you don't want to overshoot, then it's probably going to have a really long time. Now, if you have a lot of inertia in your system, we're going to talk a little bit for a second about the difference between a low inertia system and a high inertia system. Normally, you want to try and have the inertia of your motor as seen, or the inertia as seen by the motor, to be pretty close to the inertia of the motor. So if you have like a 50 horsepower drive or like a 30 kW motor, then that's going to be a pretty big physical motor. So it's going to have a lot of inertia. So it can control an inertia of a load of very similar things pretty well. You put in a gearbox, that changes the reflected inertia, and so the inertia as seen by the motor. Now, if you're not familiar with what inertia is just a physical thing's resistance to acceleration or deceleration. So it's resistance to torque. What happens in a speed controller, if you have a high inertia system, it's not going to speed up or slow down very much, right? So it's not going to be able to accelerate or decelerate very quickly. So your speed controller is like, oh, hey, I still have this error, so I'm going to output more torque. I still have this error, I'm going to output more torque. And then it's going to overshoot really bad. And what happens on a high inertia system, if you have a high inertia mismatch, like on a flywheel setup, even if you get it going, you will have to set the gain really high in order to get it going. And then once it's sitting there at speed, it's going to vibrate. It's going to sit there, and every little bitty change is going to have these big vibrations, because it's like you have to have your gain so high in order to get it moving to fight that inertia. Well, there's a thing called inertia compensation, or torque pre-control, or torque feed forward control. There's all sorts of different things, but just know that the basics of an inertia system, like the inertia of a system, is a fixed value most of the time. And if you can figure out, oh, hey, this inertia, if I want to accelerate at a certain speed, then I know I'm going to have to output a certain amount of torque just because of the inertia that is there. So you don't want your speed controller trying to figure that out if you already know it. You're smart. You're an automation engineer. You can sit there and know that, hey, this is going to take a certain amount of power, especially if a certain amount of torque to move it. And that's what this torque pre-control is. And essentially what it does is it takes the total inertia of the system based on these two values here and creates a torque based on the acceleration. You don't have to know how it does it. It's using a derivative of the change in, so it's taking the acceleration of the speed, and then it's calculating and making a calculation. So it creates a torque value that eventually gets fed in to right here. Oops, that's the wrong color. So it gets fed in from the pre-control circuit and gets added into whatever is coming from the speed controller. So this is the speed controller, right? And so this comes along this little line here, and then they get added together, and then that gets sent off to the motor. Well, under acceleration, most of the time the acceleration is just from the inertia. Like, unless you have some different load, the inertia of the system is going to be pretty much a lot of what you're doing. Because if your conveyor is 100 pounds, the box you're trying to run on it might be 10. So the inertia from that 100-pound conveyor is a lot more than the inertia difference from the box. And so if you tell the controller, hey, you need 100 Newton meters of torque in order to accelerate the conveyor, the speed controller only has to make up the torque for the box, which is a lot less than the whole system. So your system is a lot more stable. This really comes into effect when it's trying to track what's called a ramp set point, because what your load is actually seeing isn't that straight up and over most of the time. Most of the time it's a ramp. Well, if you don't have inertia compensation, what happens is this value will kind of lag and then catch up and then way overshoot. And in these kind of slow accelerating things, it'll way overshoot, and then it'll take a long time to wallow out, and you don't want that. With proper inertia compensation, this will be down here, and then it'll inject exactly enough torque, it'll speed up just a little bit, and then it'll be like bam, very tight to the set point. So getting proper inertia compensation for your system is what you really want to do. And on flywheel and fan systems, by the way, this is very important, because especially on a flywheel system, essentially all of the torque is based on inertia. You have this big inertia, and that's all the torque that's there. So on a flywheel system, if you do inertia compensation, your speed controller almost has very, very little effect. It just has a little bit based on the friction at steady state. So really cool stuff there. And inertia compensation in G120s on ACs are really just simply a ratio of these motor inertias and then a factor. And so this scaling factor, if you set it to 100%, right now it's set to 0%. 100% is going to turn this thing on until you can see that it gets injected in there. And based on these values, you're injecting more or less the amount of torque. One way that you can go through and do this is go through and see, in general, trace this value, this accelerating, sorry, not that. So with no pre-control, so 0% on this, just look at the output of this. Trace the output as you're accelerating and decelerating, and you'll notice, oh, hey, at steady state, there is 20 Newton meters of torque required, right? And when you go to accelerate, there's 120 Newton meters of torque. Okay, cool. Well, that means I want this torque pre-control to output in that same ramp. I want it to output 100 Newton meters, because I know that the accelerating torque is 100 Newton meters because the steady state torque is only 20, and the combined of that is around 120. So that's kind of the general method of just trial and error, really. You're looking at your system, you're not having to do a bunch of math, you're just looking at the output of the system and saying, hey, I'm tracing this and I'm trying to get this value. Sorry, my throat is getting quite dry. I'm trying to get this value to be the same at steady state. So like if I have a set point of 100 RPM, this torque value here, say it's, and this is just the example that I just gave, say that it sits around 20, okay? 20 Newton meters. And that's at steady state. And then I go to change the set point, and I move it, bump it up to 200 RPM. What it will look like is when I do that, it will inject in a torque, and so you'll see it jump up, and it'll be up for a second, and then it'll come back down like this. And this represents here kind of the if I were tracing out the speed, it would look like this. It would look something like this, like that. So that black line is the RPM. So this is 200 RPM, and this is 100. Okay, so that torque shoots up, and whatever this value is up at the top, that's the difference between those is the accelerating torque, and you're just trying to get that torque pre-control, and it will compensate for that inertia. Really, really cool. It blew my mind the first time that I did it, and the first time that I did it was actually on a DC drive on a flywheel. So the flywheel, I was having to put these like incredibly high P values into it in order to get it just to accelerate, and then it literally was rattling. It was like vibrating. And so again, talking back to the mentorship, I had a mentor here in the States who was an excellent DC drive, like amazing, and he actually works for Siemens. He worked for Siemens then, and now he's working back for Siemens now, but he's just an amazing knowledge base there, and he stepped me through this same process of taking this speed controller difference, like the output from the speed controller, and looking at it at steady state, and then looking at it during acceleration and making that difference, and then tweaking the values in the torque pre-control, which is something different in the DC drive, but that's really all you're doing. So that's probably more like a drives 201 topic, but it's one of the things that will make you look like a rock star if you have a high inertia system. So let's clear this out, and I dropped my notes. Clear this out. Go here. Get back to what we're trying to get to, because we're already at an hour or 2.5 hours in. I guess I just like kind of talking about this sort of stuff. So a couple of things I wanted to talk about specifically with Siemens drives, because we'll spend kind of a little bit more of this time talking about what it's a concept called BICO. So if you're familiar with drives, maybe you're not, like if you start working with drives, you are going to be working with parameters. And I switched over here in the parameter view to parameter view. I'm going to go over here and select display extended parameters, because I want to show you kind of this concept of BICO, which is the way that you connect different parameters inside a drive to each other. And so we are going to look at just kind of an example of this. I want to go to the speed set point, and I can do this. I'll show you how to get to this. So again, I'm using start drive, but if you're using starter, a lot of these pages are very similar, and you have kind of the graphic interface, the functional view, and you can kind of step through and then find what you were looking for and then go to the parameter view on it. And usually the parameters that are relative to what you're looking at are kind of all in that same area. So what I'm wanting to go through is find the set point, the actual main set point. So I'm just going back through here and tracing back. Here we go. So I want to go to the main set point here, and it is parameter 1070. I'm just hovering over it, go to parameter 1070. And if you notice, I can just show it to you here. If I wanted to inject in an additional set point, so just add in a little bit more of whatever is coming from, in this case, the PLC. This PLC has a telegram set up. We set it up to telegram 3, if I remember correctly. We can set in, hey, I want a little bit of an offset. Maybe I want to do some of that speed saturated or saturated speed controller torque limited setup that we talked about in torque sharing, the torque sharing thing. I would want to use what's called BICO, and I would want to connect in another value. And so you can see here that's BICO. These are R values, so are the read-only parameters I can put into this value. Now, I can go through and put in some crazy stuff, all right? For this, I want to just say, let's do fixed set point 1. Let's see if there's any other that's like any better. Because I'm just wanting, yeah, here we go. Let's do this. I just want to add 5%. Okay. Here's a fixed value, 5%. It's an R value, 2902, index 1. Kind of the naming scheme of these parameters. P values are parameters, R values, read-only parameters. The little inside the brackets are the index numbers. So the way I called that out was like parameter R2902 index 0, index 1, index 2, and those are just kind of sub indexes under that same parameter. So plus 5% is a fixed value here. I'm going to select that. I'm going to click OK, and it plugs that in. And now when I go to actually use this drive, whatever my main set point coming from the PLC is going to have an additional 5% added to that. So whatever the 5% is, whatever that percent is, it's going to get interpreted. We talked about reference values in the previous one. You definitely need to know that. So because this is an RPM value, that's going to be additional 5%. So that RPM is going to be off of that reference value P2000, which in our case should be 2000 RPM. So we are going. So that is BICO, and it's kind of goes both ways too. So we talked about the inputs and outputs, so like the actual hardware inputs and outputs. Okay, so let's bring an input into our drive. Okay, so we want like an on-off bit. Okay, so we want like an actual start-stop push button, and we're going to bring that into one of these drives here, or into one of our input terminals. So we can go to and do the same thing. We're going to connect from an input, our real world input, into somewhere in the drive. And so it's the same concept as what we just did with the set point, just a little bit different because it's an input. So now, because this is on the other side of that connector, we can connect this to multiple places. So say I wanted to connect this to parameter on off 1 here. I can connect it to there. I also, or let's do it this way. Let's do it this. I want my off 2 and I want my off 3 signal all connected to this one thing, and then I want to connect another one. So I can connect multiple locations. Same source can go to multiple locations, but that one location can only have one source. So it's a little bit of a nuance, but it's all depends on what side of the connector, the bit interconnector that you are using, the BICO that you're using. So I have this digital input 4 is set up as kind of your enables. So if you had like a pot selector switch, you could select that, turn it on, and say go, okay, and it goes. And this would enable everything. And we might actually want to go through and enable more, because we have enable operation, control by PLC, unconditionally release holding brake, enable speed controller. We need to set up all of these, right, for operation. And so we have this one switch that's connected to multiple places. And then it says, okay, those already have connections that are already there, and we're kind of disconnecting those connectors. That's what this is like warning us about. So we're going to say okay. And now if we wanted to actually do an off 1 here, that would be here off 1. We could do that. Now I have this set up as Profinet control. So all of this other stuff is also going over Profinet. I'm just showing you the concept of the BICOs right now. Really quick portion of it, because we're already at 2.5 hours. It's kind of crazy. So far it's been really cool. I'm glad that everyone that's been on has hung out. If you have been hanging out through all this, yeah, thank you so much for taking part of these live streams. It's really fun to be able to kind of just work with people, and yeah, like I said before, spread what was given to me. So we'll save that. What else was it? What did I say in my? There was something else I feel like I'm missing. Let me look up what I'm actually supposed to be talking about, because I didn't have it in my notes. I honestly didn't think that I was going to get this far. Or sorry, it was going to take this long to do everything. So let's go to content, and this music is kind of little a little all over the place, isn't it? Oh yeah, the fun stuff. So, common faults and how to troubleshoot them. So, common faults and how to troubleshoot them. That's what I put in the description. So, I'm going to go through and I'm going to kind of show you some of these common faults. Let's see if I can... We're going to swap over for a second. So, swap up here, and I want to get, because I want my bigger screen for me to see. And so I'm kind of like looking up instead of looking down. But what I wanted to do was get down in the bottom right, down here, like that. We're going to go to some help files, and let's see if we can, I could show you if there's a good way to get there. Because there's a lot of times where sometimes your faults that you get, I wanted to go through because there's a couple of faults that really come up a lot, and I wanted to show you the like diagnostics on them, like the actual help files themselves. And it doesn't. What I may have to do, I may have to cheat. We may have to go into starter to show these. So starter has an easier way to get to the help files because you could just type in a fault number. I haven't quite figured out in Start Drive. If anybody knows how to get access in Start Drive to the fault numbers in Start Drive really easily, then let me know, because I know like all you have to do I just brought up starter, and so this is the HTML help for starter, and so like I can go to like fault 0, so F0701. I say that and then it's not gonna work, right? 7002. I guess hold on. Let me of course it's not gonna work. Maybe there's not enough zeros. I think there's not enough zeros. Nope. Still blings. So we may just go to the list manual. Do it that way. There is always ways to get to the faults, right? So if you're not aware, there's the end all. It's called the list manual. This one is for the S120, but we can kind of go through those. Yeah, Lucid, thanks. Guess whose system that fault 31118 was for? The bane in my existence. By the way, if y'all are watching this, Lucid is one of my real life customers, so he gets to give me even more pain and trouble, because yes, any pain and trouble he gives is my own fault. But yeah, so gotta go through some of these fault classes and stuff, because there are a lot of faults, and as Lucid is bringing up, fault 31118 is an encoder problem. And a couple of things about kind of the nature of these fault numbers. You have some faults that are in the, those are 70,000. That's why I'm missing them. So you have some numbers that are in the orders of like those 30,000 parameters that he kind of oh yeah. So we're sharing in the pain of the 3100 faults. 3100 faults are those encoder faults, and we had some cables. We installed some equipment at one of their plants a couple months ago, and apparently we had some cables that had some stuff that got dropped on some encoder cables and give some really crazy noise-based faults. And The 30,000 numbers are hardware level faults. So 30,000 faults are based on things that you cannot do anything about. And I really wanted to talk about this motor blocked fault 7900, and it is probably, if there is one fault for you to recognize, is this fault 7900 in the Siemens world. So if you didn't know this, I spent the better part of 10 years as a drives and motion specialist for a Siemens distributor here in the US, and I was kind of the drives guy. And the first thing that I learned is this fault 7900 can make you seem like a wizard, okay? Because this is the one that, like, most of the time will catch up to you. You'll get it when you're commissioning. You'll get it in some like random times, and it seems to be the thing that's like, oh, hey, I'm getting this fault 7900. What could it be? And you don't even have to, if you just remember, oh, motor blocked. That's a motor block fault. That's 7900. What this means is that the shaft either cannot move, so the motor cannot move, or it thinks it cannot move. And so, yeah. See, we have someone in chat that is having a fault 7900 right now, because it's probably the most common fault for a drive system that's so you're either jammed up, or if you're starting up your system, like if the system has never ran, the encoder signals can be reversed. So like if you don't have a Drive-Cliq encoder, it doesn't know, like, you can put all of those terminal wires in, and the encoder pulses could be pulsing in a clockwise direction, and the shaft could actually be running in a counterclockwise direction. So what'll happen is the drive thinks that it's supposed to be running counterclockwise, and then all of a sudden the encoder says, hey, I'm running clockwise. And so what it does is it says, hey, I'm running the wrong direction. I need to put more torque out in the clockwise direction. And so the encoder says, no, you're running in the wrong direction. And so it's this feedback loop that immediately it torques out. It goes to a maximum current and says, hey, nope, I'm jammed up. And if you're not moving fast enough, you'll get this 7900. So 9 times out of 10, though, your system's already running. And then if you're getting this 7900, most of the time it means that there is physically something that is jamming up. It's hanging up. You've got some sort of like chain that's catching on an edge. You've got like a belt conveyor that is sagging and it's hanging on something, and it's just running so slow and it jams up. Or if you have a pump system, for example, and you have a deadhead valve on your oil loop, and your maintenance guy deadheaded off the thing that you're working on and you didn't know about it, and all of a sudden your system that was running perfectly yesterday, now when it goes to start up, it throws this 7900 every time. Well, a maintenance guy will be like, hey, your drive's messed up, it's throwing out fault 7900, come out here and fix it. You should know 7900 means that something's mechanically wrong. If you have a brake that's not coming off, like a wire's broken on the brake, you're not turning on and off a brake, you have a valve that's deadheaded. If you get a 7900 on a pump system, just ask if all the valves are open. Just first question, ask if all your valves are open. The first ever drive system that I started up was actually out at Lucid's plant. I think it was before he was working there, but they had like an oil circulating system, and it was in a commissioning state, and so they had deadheaded the valve, and this thing gave me so much trouble because I'm like, what the crap is going on with this? Like, this was running yesterday, and sure enough, it was a maintenance guy that had gone through to deadheaded a loop. So another reason that you can get this motor blocked, and is kind of like with Christian's example here in the chat, is that if you try to accelerate or decelerate too quickly at a slow speed, because motor blocked has a speed threshold. If it's underneath a speed threshold, then this motor blocked fault can crop up. If it's not, then you'll get the 7902. So motor stalled just means that it's in torque limit. Well, sometimes you want it to be in torque limit, right? Like, we've talked about many different applications where you'd want to be in torque limit. But back to this 7900, if you're trying to speed up or slow down too fast, you're in this motor block threshold range. So it's in 21P2175 right here. Then so he's saying, I'm using a sensorless vector control setup and controlling motor via joystick, controlling speed output via potentiometer. Oh, that is a cool application. So if you're flipping back and forth, so probably what you need, you have a dead, you need a deadband in your joystick. Because if you're going back and forth, you're at a low speed, and you'll be at a low speed, and then you're going from something positive to something great negative. And so there needs to be a range in there that's a 0, to where the controller can actually ramp down to 0 and then ramp up to negative whatever. Because what happens is, if you go into torque limit, then, and you're lower at this low speed, then you will get to 7900. Now, by default, this 7900 is like speed threshold is set kind of stupid low. So look, we have the motor has been operating at the torque limit longer than the time specified in 2177. Okay. And if you notice, this is the list manual for S120. If any SINAMICS drive, if you have the same control loops, if you have the same thing, those parameters are going to be the same if they meet the SINAMICS specification. So I can go into my G120 here, and go to, what was that, 2177? I have the memory of a goldfish. 2177. Go here, go to parameter view, click here, 2177. The motor block delay time. And so for on this one, it's not too bad. It's 3 seconds. On a servo control, sometimes that is like 0.1 seconds. It's kind of like stupid fast. And so so I would ask you, kind of Christian, in your application, do you know what this 2177 delay time is set to? Because if it's set to 3 seconds, then what you may have is a jitter jumping back and forth between positive and negative, and you're only running a couple of RPM, and you're jumping back and forth between, say, 7 and -7 RPM, something like that. So if you're taking in those inputs, create a deadband around 0 that if it's saying to run less than 10 RPM, something like that, and then, yeah, so if it's, I mean, there also is a way, I mean, pretty easily on this to disable this function. And yeah, no problem. This part is kind of the fun part, like mentoring tip type stuff, because a a lot of times these things can be just kind of like annoying, and other people have kind of dealt with these same situations. Yeah, I would make sure that inside a deadband first, like coming from your controller, coming from like your joystick, that anything less than like 10 RPM, it's just going to throw out, so that joystick will have drift in it, and you're just not bouncing back and forth, because yeah, it can do this. Second thing, you can decrease this fault 7900. Yeah, these are some crazy ones. I mean, this 7900 it simply means you're going into torque limit and you're below a threshold. So kind of like torque limit means like it's trying to run backwards, and like I said, it's the fact that it's in torque limit for that long. If it's still 10 seconds, what could that be doing? Because that seems like a long time for this to be doing that, for it to be getting a 7900. To go forward and reverse really quick. If it's 10 seconds, huh? So if you were going from one side to the other, and like actually going from like a negative 100 RPM set point and then flipping over, your deceleration rate, so your 10 seconds. Okay, so this is something here that 10 seconds would have to be greater than like this value, P2177 would have to be larger than your deceleration rate for your drive. And it's your and center, then forward again really quick. We cause this. Okay, so if you push it forward, then center, so that's going to a 0. And then forward, cause this. So it's going to a torque limit. I mean, huh. But if you go slow, then it's fine. Yeah, that is a fun little problem. And by fun, I mean drive you crazy. It almost doesn't seem so. Decel is 4 seconds, so that should work. Because what'll happen, so something else is going on, and it's always 7900. It's never 7901 or 7902, because the only difference between 7902 and 7901, or sorry, 7900, is just the fact that 7902 happens when you're moving faster. So, I mean, there's a couple of other ways that it could do it, but 7902, just in general for everybody else, is if you're running and you go into torque limit, like you put too much on your conveyor, or your kind of your drive, like the fluid heats up or actually cools off. So if you're like pumping oil and oil cools down, then the viscosity is gonna I guess it's lower viscosity, and so your load is going to increase, and so you might get a motor stall to 7902. So something like that. But with this, let's see, what could it be? Let's kind of look at this, because your torque limits, I mean, honestly, I shouldn't, or Christian, you need to join the Discord, because I want to make a suggestion that I don't want to put on YouTube. Because because there are ways to go through and kind of bypass some of these things, and this fault is really intended for you not to overheat a motor or kind of like damage a motor. Most of the time when you're doing this motor blocked, it's because something is jammed up. But in your case, it might be a byproduct of something that is like natural in your system that just doesn't make for proper usage for this. And so what'll happen is so there are ways that some functions, some of these faults can be disabled, because there are a couple of control modes to where this function in particular needs to be disabled, because in EPOS there's a mode called travel to a fixed end stop. So say for example you were driving some sort of like a proximity sensor or something, and you want to push it up against and put a certain amount of torque up against kind of a wall or a part. So there's kind of this application called a fixed end stop where you're wanting to kind of drive your motor and push a certain amount of torque up against it. Well, if you did that, you want to put it into torque limit and you're not moving. Well, obviously that's the whole design of the system. Well, fault 7900 would every time, just over and over and over again, every time you did that, it would fault out. And so there are ways to disable that. I definitely don't want to put those into kind of a 102, because most of the time, if you're getting a fault, there's a problem. Siemens is really good about, if you disable one of these faults using these techniques, if there's actually another problem, it's going to fault out on something else. And then if you disable that, it'll fault out on something else. And then it'll get down to something to where you can't disable it. Like that 31,000 fault that Lucid was talking about before, you can't disable that fault. You can't just ignore it. It's a hardware level fault. So, yeah. And so it might just be that you need to disable this fault for that. Because if it's only ever doing 7900, then it's probably just something that's like, it's putting it into the torque limiting. But honestly, 7900, usually if you're starting up, it means either your motor's running the wrong direction or your encoder's hooked up backwards, because the encoder's saying it's running one direction and the motor's actually moving in the other direction. And so that'll be a problem. And then if it has been running before, except if your name's Christian, apparently, most of the time it's a physical problem. Your brake's on, you've got a valve deadheaded off, something like that. And so just put it in your memory. If you see a fault 7900, and a maintenance guy is coming up to you, like a mechanical guy, and he's saying your drive is bad because you've got a fault 7900 that keeps coming up, this drive is crap, you could ask him these mechanical questions, because odds are it's going to be a mechanical issue 9 times out of 10. But kind of like I just said, sometimes we actually want it to go. So if you notice, these 7900s are about motor speed, and so it's about things that are like you're not really doing what you're supposed to be doing. And so but yeah, so honestly, I probably talk about these for a lot longer, but we are sitting at 3 hours, and honestly, this is what I wanted to talk about, just in terms of troubleshooting and setting up and kind of like a Drives 102 class, especially with Siemens. Again, I have said multiple times on the stream, like, I appreciate everyone that has joined in these communities as we've been growing. We've got multiple ways to join in, and now to where we've got the Discord that's up and going, and it's been growing. We have people kind of talking all the time, multiple people working through issues in that community. We also have the live streams, we have comments on the videos on demand, and we have the edited videos. And again, if you're on here and you haven't liked this stream already, please make sure that you like it to get it out there. That actually is an incredible way to support these channels, is by chatting, dropping comments, all these different things. Really gets the channel out there. We opened up memberships this past week, or actually a couple hours ago, I think. Got everything set up. I will be putting everything that we do, all of the project files and everything that we've messed with will be available for members at different levels. And I will try to make that worth it. And if I don't feel like it's worth it in a month, I'll give you some extra stuff. Because I'm all about making sure to provide value to you if you are asked, or if you're paying for something. But if you haven't yet, and you've liked this video and you've liked these channels and it's helpful, okay, so I will update the Discord link on the chat for this one. So probably what happened, yeah, it's probably expired. So I will update the link on Discord in the description here in a second. And yeah, so you can join in on Discord, we'll do that. If you like these videos, please make sure you're subscribed and get them out there. The YouTube algorithm gets it out there. I'm sure that there are other people that can benefit from these too. And yeah, I will get everything updated. I appreciate everyone that has joined in today. I hope you have a great rest of your week. And yeah, many different ways to get in touch if you're having trouble. And yeah, always keep that humility in your mind, and that willingness to learn from anyone about anything. And until maybe later this week, I will talk to you later. But yeah, so